Hello and welcome to Fluid Mechanics. This video is going to focus on a specific example for treating planar surfaces exposed to a fluid. And we previously talked about the fundamentals of this situation in the last video of this series of lectures, but we're going to give you a concrete example, and I hope you see that it should work exactly the same for any situation of a planar surface exposed to a fluid. So here we go. So over on the left hand side here we have a water retention system, and we're primarily going to focus on this pink gate here that's composed of a hinge at A, and it's being held in place by a retaining wall at B. And we want to focus on finding the reaction force at B that's holding it in place. The gate's weight is 10 kilonewtons and its dimensions are 2 by 2 meters. And why would you want to do this? Maybe you're designing this retention system and you want to verify that your wall's strong enough or your stopper's strong enough over here. Just double checking things. So that'd be why this is important. Okay, so the big thing about this example is pressure and how it kind of works. So let's just recap 3 highlights of pressure, and I think we can dive right in. So pressure has 3 key components. Number 1, it acts in all directions equally at the point you're considering in a fluid. Number 2, we can calculate the pressure at a point in a fluid by considering what the fluid is, and that's designated by this density value times gravity. Or you could just do specific gravity, so these are 2 equivalent expressions. But also, maybe the most important thing is it's dependent upon the depth within the fluid. And this depth is measured from the surface down to the location in the fluid that you're concerned about. And lastly, pressure always acts perpendicularly to any surface. And we're going to show this on the left-hand side here. I'm going to show the pressure distribution here. So our gate will have the left-hand side at a shallower location and the right-hand side at a much deeper location. And because of our relationship over here, our equation for the pressure within a fluid, we know that we're going to have the left side at a lower pressure and the right side at a higher pressure, and we know that it varies linearly with the depth. So there's going to be this smooth transition, gradually increasing pressure as we go down. So that's nice. Okay, so how do we use this to go and find our force at position B? Ultimately, we're going to treat this as a static equilibrium situation, and we're going to do some special things with this pressure distribution. So first off, I just give you some details. If we're looking straight on at the gate here, shown by this little creepy eyeball here, it's going to be a 2 by 2 as stated in our problem statement. Okay, we're going to define the y direction as the vertical and the x direction as the horizontal. Okay, and we're going to use a free body diagram to analyze this. And basically, we're just going to look at all the forces and torques acting on this thing. We know that at the top we have a hinge, and a hinge only allows rotation and does not allow translation right or left or up and down. We know that this uniform system has a weight that acts downwards at the centroid, and we know that down at the bottom we have a contact force with this wall, and that there's going to be a normal force there acting perpendicular to the surface of the wall. And lastly, we have this pressure distribution, which is the kind of new weird thing we're looking at here. Okay, so let's go into the details how we're going to treat this pressure distribution here. So because we have this pressure distribution, we can model all these different forces happening here as one resultant force. And because the bottom of this gate is going to have bigger pressures or forces than the top of this, it's going to skew this resultant force down toward the bottom of this gate. And that's nice, but this magnitude of this force can be kind of tricky to calculate, and also exactly how far skewed down from the centroid it is can be kind of tricky too. So in the previous lecture, we described the fundamentals of how we could model this equivalently, and here's just a quick reminder for you. We can model this pressure distribution as a pressure force acting at the centroid and a couple acting at the centroid. And just working with the center of something is always a lot more intuitive and easy, so we're going to use this. So we can go ahead and replace all this green pressure distribution by a pressure force and this couple acting at the centroid. So let's go through the details. Let's figure out all the things happening here, and ultimately we're going to solve for the normal force acting on this. So first off, we're going to talk about that pressure force over here. And as we go here, we already described how to find the pressure, but we're going to be finding it specifically at the depth of the centroid. Right here is where we're going to model this acting at. Okay, and a lot of these values are straightforward, but this depth is slightly tricky here. So how do we get to this centroid right here? Well, we got to go down 1 meter, and the vertical distance from top to bottom has already been defined for us as √3. So we're going to be 1 plus half of √3 down. Now hopefully you can appreciate how I came up with this. Ultimately, you get 73.15 kilonewtons. All right, let's go to the next thing, the couple. So the couple we model as the specific gravity times the second moment of inertia times cosine beta. Okay, and so let's look at the details of that. And so the second moment of inertia for a rectangular object is pretty commonplace, and you can go look that up easily enough. It's going to be 1/12 base times height cubed, and we're going to be going from the center horizontal axis here, as defined over here. Okay, now cosine beta is going to be this angle between the surface and the vertical right here, and let's talk about that. So when we put in the specific gravity, we put in our information for the second moment of inertia. We have this funny little part over here, cosine beta. Now we know that cosine beta ultimately is just a ratio of sides. It's adjacent to hypotenuse. So if you go up here, and this is a little bit tricky, but you could maybe envision here a right triangle that looks like so. Okay, and the adjacent side is just going to be this vertical leg, and the hypotenuse is right here. We know the hypotenuse is 2, and we know that this is going to be √3 for that vertical leg right here. So over here, hopefully you can appreciate how we can just substitute in, instead of cosine of an angle, we can say, hey, it's the ratio of two sides of a triangle. And we get 11.32 kilonewton meters. Now, we have everything we need to go through and conquer this little problem here and find our normal force acting over here. So let me lay it out for you. So we're going to do torques about this point A over here. Okay? And so it's in static equilibrium. This gate isn't going anywhere. So we're going to go ahead and walk our way from this top point on down, accounting for all the forces and torques acting on this thing. And we should be able to solve for normal force of B. So let's do that. So right away, we have at the top, we have forces acting here, but they're actually acting exactly at the point that we're summing torques about, so they don't have any moment arm. They're going to produce 0 torque. Next, we have the weight. Okay, and we know the weight always acts downwards, and for this uniform object, okay, it's going to act at the centroid. Okay, now when we're doing torques, it's the perpendicular distance between the point of rotation and the force being applied that's really important. So that perpendicular distance would be from here over to our vector, okay? And if we look up here in some more detail, we know that's kind of like this distance, okay, which is 1, but we're only going halfway over because the force is being applied at the center. So that's going to be half of 1, that's going to be a half. Now we have the pressure force. Let's talk about him. Now he's acting the same point, but he's in a different direction. We know pressure always acts perpendicular to the surface, okay? So it's already perpendicular. We already know this length of the gate is 2, so the perpendicular distance between this point and our applied force is actually going to be 1. Hopefully you can appreciate this 1 here. And we have a couple, and we have our normal force here at the end. So remember, for torques, it's the perpendicular distance that's important, okay? So this normal force is horizontal, and I think we already have, so the distance that's important is from where this is applied to upwards, okay? And we know that that's going to be root 3, isn't it? Root 3 for the perpendicular distance here. So hopefully you can appreciate where this root 3 comes from. And these are concepts you should learn in your first physics class, okay? Just a little refresher for you. Okay, so let's see what we got. We've already previously defined our couple, our pressure force, and our weight. So we have everything we need. Plug them in, solve, and we get 45.88. So let's go ahead and summarize what happened. Okay, there's 3 big things that are important here. We have this weird pressure distribution thing. That's the new cool thing we're learning about. And so we know it's related to the heights, and that the heights of this, the depths change as we go down. There's a linear relationship. So that explains this nice kind of pattern we have for the pressure distribution. But the cool thing about this example is once you do one planar surface, it's like the same for all planar surfaces. Whether it's vertical or we have a horizontal plate here. Now, just real quick, I'm kind of simplifying here. We're only looking at one side of this, of these plates in this surface. The other side would just be a mirror image. But regardless, however we look at this, we know that the force, the pressure distribution is always going to kind of look similar, except when we orient this surface so it's more vertical, it just makes there a bigger pressure difference between the top and bottom, and it skews that force further and further, the resultant force further and further down towards the bottom. As you go more towards horizontal, it's going to make that resultant force go towards the middle, and it's going to make it a constant pressure distribution across the top here. Okay, and then we came up with this in the previous lecture, this method to have an equivalent modeling. And we can replace that resultant force, which is kind of tricky to deal with a couple and pressure force at the centroid. And lastly, we said we can use a static equilibrium treatment. Since we're only looking for the force at B, we did torque. If you wanted to figure out the forces at the hinge, you could do forces in the X and Y in equilibrium. Thank you, and I believe you should have lots of confidence approaching any other example of a planar surface exposed to a fluid.